Assalamualaikum. In this video, I want to share with you how we simulate STM32 chip. Yeah, this chip is actually STM32 F103 CC. This STM32 F103 use Cortex M3. But on our class, we study Cortex M0 Plus. If you study in deep about the Cortex M0 or M0 Plus, all the instruction that support by the M0 and M0 Plus is also support by the Cortex M3. So that's why I allow a student to use this Cortex M3 to simulate what we have learned on our class. Even though we study for Cortex M0, but the same knowledge, the same syntax, the same instruction set, we can simulate to Cortex M03. Okay, but we need to do some modification for our circuit. Here in this circuit, I use port A. I connect all the port A starting from port A0 until port A15. Here port A0 until port A15, and I connect to resistor and then to LED. The function of this resistor is to limit the current. When current flow from here is represent power connector. Power will flow, current will flow from here, and then will go through this LED. We light up this LED, and then the amount of current will be limited by this resistor, and then the current will go to this pin. So we can say that this LED will turn on when this pin is at logic 0. Okay, now let's go and let's see our coding. KEIL. Okay, here I write this coding in assembly.s. If you write the coding, if you write our coding using C, your file should be .c. But here .s to represent that this coding was written in assembly. Okay, first thing first, if you remember the flowchart that I shared with you 2-3 days ago, this one, yeah. Process to initialize microP is start with set the RCC register. Okay, reset and clock control register followed by the GPIO register, general purpose input output register, and then ODR register. Okay, here is the address. RDC address is 018. Actually is referred to the offset value, offset from the starting address. So this address for port A GPIO, port B. So inside the port A, we will see this 7 register: control register for low, control register for high, IDR, ODR, BSRR, and etc. And the address for all the register was parked inside this address, starting from 800, 804, 808, 800C, 810, 14, and 18 in hexa. Now let's see the coding. Here we start our first line with set the RCC register, RCC APB2 enable register. And this is the actual address for 002100018 is an offset. So we can write like this: 1000 plus 8. Since 18 is an offset for APB2 enable register, the RCC register is start at address 4000 to 1000. Okay. Okay, next we program the GPIO, general purpose input output for port A. Okay, we start with the set the we program. Either we want to this port A to become as a output or input, but this is only the address, meaning that when I mention on our program GPIO underscore CRL, it's referred to this address 40010008, and this is address for CRH, for IDR, for ODR. Here is stack to tell the compiler the size of our stack, and then followed by the interrupt vector. Here is the interrupt vector, meaning that when we reset our system, we want to tell the computer where to go or which program computer will execute. Like this one. For the first interrupt vector is to represent the initial stack pointer, refer to starting address for the stack pointer. Second is reset handler. When we reset our system, microP will execute program starting from this mark, okay, or this label, reset handler, followed by the non-maskable interrupt handler, hard fork, blah 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 blah. Then all this is refer to the interrupt vector, and here is the start for our program. Here is the reset handler, meaning that when we reset our system, microP will straight away jump to execute starting from here. Why? Because I marked this label reset handler to represent the first program after reset. Okay, so first program that microP to execute is initialization. Initialization what? Initialize the reset and clock control. Yeah, here start with RCC register followed by the GPIO. So first thing first, I load address for RCC APB enable register to R0. What address? This address. Okay, microP will assume RCC APB to NR is equal to this address. So in this line of programming, microP will copy this address into R0, and then here microP will copy any data from that address to R1, and then microP will load data 0004 to R2. Next, it will OR R2. Here, let's see what happened inside this APB to enable register. Okay, APB2 enable register, not this one. Which one? APB2 here. APB2 to represent is a register that control the clock signal for the entire system. This one, pin number 2 or bit number 2, 012, is in charge on input output for port A. If we want to use port A, meaning that this input output we need to write logic 1, meaning that we need to enable here pin number 2. Here, input output port A, input output for port A enable. If we write 0, meaning that we disable. If we write 1, meaning that we enable that port, meaning that we enable port 0. If we want to enable port 0 and if you want to enable port A and port B, we need to write both bit number 2 and number 3 with logic 1. So if we want to activate or we want to power up these two port, both this bit, we need to write logic 1. So the value that we need to write here is 1100 is equivalent to C, and all any other port is 0, 0000, 0C. But on my case, I just want to activate, or I want to enable only input output for port A. So I write 0100, I write 04, meaning that 04, 00000004. So that's why on my coding you see I write 4 here. Next, I OR this value from R2 with existing value inside R1. Existing value meaning that any value that already written on this register. So when we OR, the original value will remain and the new value will be slot in. So it will not in it will not what we call it, modify the existing content inside the APB enable register. Okay, and then I store the modified value into the R0 into the APB enable register. So that after this 5 instruction is complete, I manage to uh, enable port A. Next, I program a GPIO. Here, second step, you program a GPIO. So the register involved is CRL or CRH or both. IDR register if we want to read any value from switch. ODR register if we want to write any value to output, either the 7 segment or LED. Okay, so here GPIO, I write all 3, meaning that I want to program port A for pin CRL. Let's see CRL register. CRL. GPIO CRL here. CRL is control pin starting from 0. Port X. In this case, we use a port A configuration for bit number 0 until 7. Meaning that for port A0 until port A7. How about port A8 until 15? It will control by CRH. Control high register. Okay. So in this case, this 4-bit CNF 0 and mood 0 is used to control pin number 0 for port A or port A0. Okay, mood here. Mood here, if mood 00 here, if mood both 00, meaning that general this pin will function as general purpose output push and pull. You already learned about push and pull output on your digital electronic. If you write 01 here, meaning that general purpose output, but in the open drain format or in open drain circuit. Alternate function for mode. Okay, uh, this one is for output mode, but for input mode, 00 is represent to analog input. Analog input if you deal with a digital, analog to digital converter. For Y, mode, sorry, this one is CNY, this pin, CNY. So on my case, I want to program this pin to become as an output. So I need to write 00 or 01. On my case, I use 00. 00 to program this pin as an output pin. And then for mode, 11 is if I want to set that pin so that that pin can on off up to 50 megahertz. If the frequency is lower, we can set only at 2 megahertz by write 10. So on my case, I use 0011 00 to represent output, 11 to represent 50 megahertz. So the value will be 3. Here I write 3. So for port A0, 3, port A1, 3, port A3, 4, 5, 6, 7. All port is considered as an output pin. Okay. But for C hard H, meaning that for pin number 8 until 15, I use 7. What is 7 represent? 7 is represent 0, 1, 1, 1. 0, 0, 1 represent the here 0, 1 general purpose output open drain, 1, 1 frequency 50 megahertz. So all will be 7 like this. So after I finish configure, I can start application. I load value from ODR. I read value from ODR, and then I write a new value to ODR. This one is load address for ODR into R0. I load my new value data value F0, meaning that I want to send a logic 1 to bit number 3 until 7, and logic 0 to bit 0 until 3. Because 0 here in hexa is represent 0, 0, 0, 0, meaning that bit number 0, bit number 1, bit number 2, bit number 3, all 0. And here FFF represent 1, 1, 1, 1. Bit number 4, 5, 6, and 7 will get logic high. And then in this case, I store the value to GPIO ODR, and suppose after microP execute this instruction, we can see that our LED will turn on. Okay, and then I call for delay. This is a subroutine. If you remember when we study about subroutine, branch link delay is considered as a subroutine. So here microP will jump here and then execute. We load this value 100,000 in hexa to R7, and then subtract 1 until the value, all this value will be subtracted to 0, and microP will loop here, loop again and again and again and again. We can say that here microP is leaping, doing leaping. And then BX, branch exchange to link register. Link register to tell the microP this program will return back to the previous point before microP execute subroutine. Next, microP will read a new data. Previous data is F0. Now the data is FF. So first we send logic 0 for bit number 0 until 3. Now we send logic 1 to bit 0 until 3. Okay, and then the same process happen. We call delay again, and then we loop. Here is, we can say that here is infinite loop. Or if you use C, we can say that while. While condition is true, while 1, we repeat this process. Okay, so we build a program, 0 error, and then let's go to KEIL. Here, okay, I forgot to tell you. If we want to simulate this program, we need to instruct KEIL to generate here hexa file, to create hexa file, meaning that the program will be converted into hexa file, and this hexa file will be used by the Proteus. Here in Proteus, we need to link this program here. Program file is this template assembly language.hex. Okay, after we link the program, and then now we can run the simulator. Okay, you see that these 4 LEDs blinking. This 4 LED is referred to port A0 until port A3. Here you can see it changed from red to blue to indicate that the logic value is changing from 1 to 0, and then 1 to 0, 1 to 0. Okay, here this LED will turn on when here is logic 0. Why? Because current flow from here is connected to 5 volts, and then it's returned to 0 when the logic value is here is 0. When red, the LED will not turn on because the voltage is balanced between this part and this part. Okay, let's see what happen if we modify the program. Instead of here I send F0. What happen if okay, before that, let's see what happen if I increase the delay. Instead of 100,000, I use 800,000. Meaning that I ask microP to do extra time for lepak, extra time for 2 ways here. So rebuild file. So we need to rerun the simulator. We need to stop and then okay, rerun the simulator. So the delay will increase. The delay process will increase. Okay. Before this, you can see that the blinking process is faster than this. Okay. So I changed back to 100,000. So I change the value. Instead of F0, I send A0. A0, and here 5F. Let's see what happened. Build file. Rerun our simulator. Stop. Okay, rerun our simulator. See, here's changing from A. A is when 1010. Here is 50101. Okay. Okay. So guys, meaning that now we can use our program to manipulate this circuit. If you connect this computer to your board, to your Freedom board, you can see that the actual LED that you connected to the board is blinking at a real time. But here for simulator, of course, it depends on the CPU loading. If your CPU is running a lot of program like mine, you can see that the process and the blinking is not according with the real time. Yeah. In this case, I've also connected to the 7 segment. The 7 segment I also connect to a port A0, port A1, 2, 3. That's why this 7 segment display is changing in line with this 4 LED. Okay, from F here, if F here is now 0 because all 0, 0, 0 represent 0. This one is a BCD, binary coded decimal 7 segment. Okay, so actually this is what I expect you to do on your project for 20% for 20% marks. You need to study manuals. Yeah, you need to study manual for understand the configuration, which register that we need to modify, and etc.